Hello, my name is Toni Bailey from TB3 NDT Consulting LLC. I am the owner of this company and a managing member, and I am an ASNT level 3 for non-destructive testing. And I'm showing you a slide of my contact information here. If anyone needs to contact me, my information is shown on this first slide, and also the last slide will have my email information. So let's get started. So I am an ASNT level 3, and I am certified per NAS 410, which is a national aerospace standard. And I am certified in the methods of metal etch, radiography, ultrasonics, eddy current, liquid penetrant, magnetic particle, and I'm an ASNT level 3 for the radiation safety credential of IRRSP. It's a national standard. So nonetheless, our company provides NDT classroom training, examiner services, hands-on training, and audits. Now, I want to thank you for joining our presentation, which is titled Bridging the Gap Between NDT and Aircraft Maintenance. And if you know anything about non-destructive testing, the difference between non-destructive testing and destructive testing is destructive testing is using like tensile test or shear test or contortional tests to test the strength of the metal in manufacturing. But non-destructive testing uses different applications to find stress cracks, corrosion, and any other types of abnormal conditions. We use scientific methods to find these conditions on aircraft. So for my PAMA presentation, by the way, there's a lot of NDT methods that you can see, like the ones I'm certified in, but I'm focusing this presentation on digital imaging, which means radiographic digital imaging, and ultrasonics for NDT. And I'm going to tell you a little bit about those techniques or those methods as we continue this presentation. So the purpose of this presentation, this is a 45-minute presentation to provide a broad discussion applicable to aerospace composites and the challenges in developing NDT techniques for those composite structures, using non-film digital radiography techniques for composites and the type of discontinuities that are detected. And the third area that we're going to discuss is ultrasonic techniques for composites and the types of discontinuities that are detected there. Because for composites, most of the techniques that we use are radiography and ultrasonics to find discontinuities. I'm using this presentation to share with you guys that we're using advanced non-destructive testing techniques as opposed to the older conventional techniques, which I will discuss in the presentation as well. Now, I said this is a 45-minute presentation approximately. If anyone that's attending this PAMA presentation, if anyone has questions, you can email those questions to Toni, T-O-N-I, at tb3ndt.com. So buckle your seatbelt because we're going to go on a journey and it starts right now. So for FAA applications for in-service aircraft, I'm going to focus this discussion specific to inspecting corporate jets, as you can see here. I'm going to use a little bit of annotation here to kind of highlight some areas. Corporate jet inspection, military aircraft, like this F-15 fighter jet shown here. And as a U.S. Air Force veteran, this is an aircraft that I worked on a lot in the Air Force. And we inspected, wing tips, flight controls, the vertical and horizontal stabilizers there. Those are composite structures, even this area of the canopy, and also some areas of the intake. So pretty much, I don't want to say like 70% of this aircraft is composite. And a lot of corporate jets are composite too, which is why NDT inspection is so important for these aircraft. For commercial airliners, to make them more lightweight and aerodynamic, We also are manufacturing those out of composite structures, pretty much the same areas as military aircraft. And also, I threw this in about engines. Aircraft engine coverings, which we call cowlings, are made from a lot of composite structures. I'm going to talk a little bit about that as well. So here we go. Let's go to the next slide. Now, what are composite structures? You may ask yourself. Composite structures are areas of the aircraft that or metallic attached to another metallic, we call that bonded, or made of different layers, such as, and let me use my tool here to show you these, to highlight these areas, Kevlar, honeycomb sandwich structures. And this is a Cessna Citation 10 right here. You can see this area right here down below. Citation 10 airplane figure. The red areas are made of Kevlar. And so that is a man-made material that could be layered together to make a structure. The yellow areas are graphite honeycomb composites. Sandwiched together means that you take several layers and bond them together. Generally, adhesive bonded areas are the orange areas. And that means you take a couple of thin metal materials and glue them together, as shown here in the green as well. Fiberglass materials is in light blue. Aluminum skin, very thin, like 25 or 12 thousandths, bonded to honeycomb, or even just straight up Kevlar. So as you can see, we have a lot of areas that are very lightweight on this aircraft here, this corporate jet. Here's a picture of what I was talking about. You can have a thin aluminum over here to the left. Let me use my annotation to show you. Like 12 thousandths, 0.012 thousandths bonded to 0.025, 25 thousandths. And this hatched area here is the glue line. And then you have honeycomb structure. It's typically called a Nomax core, which means they make paper products and glue, and which we call resin, and make this honeycomb shape. Or carbon fiber, which is very thin layers and strings of carbon that are woven together to make a splice. And this one right here is from this is a Sikorsky helicopter rotating component. So it's very strong, but it's also very very good for twisting and turning and elongating. So it makes it easier to manufacture. Like this hybrid boron right here. This is a woven fabric that's actually making a fuselage structure. Isn't that something? The entire fuselage right here is made of this woven fabric. I remember one time I was inspecting one of these aircraft that was made from this hybrid boron there, and strings of layers was hanging from the wing, and I didn't even know what it was at the time. So as an NDT person, I said to myself, what in the world am I inspecting? I have to come up with a good technique to find the delaminations and the damage to this inspection. So, excuse me, damage to this aircraft wing. So what are the challenges in inspecting composites? Well, we in NDT still have a learning curve for NDT of composites. We have to ask manufacturers, what materials are used to design or manufacture this aircraft? Because they're designing them and manufacturing them faster than we can learn techniques to inspect them, because some of the older techniques are not sufficient for testing these new materials. So as FAA NDT inspectors, we have to understand the customer's aircraft type here, the airframe design, the composite type, and the type of inspection that's needed. We have to know, what are they trying to find? And based on this, we select an optimum NDT method and the specific equipment for technique development. So as a level 3, I usually get involved with making these techniques and working with the manufacturers to make them work better so we can find the flaw of interest. Now, for developing the technique, I have to consider the following. The aircraft manufacturer should have specifications that's based on ASTM, which stands for American Society for Testing Materials. So the aircraft manufacturer goes to the ASTM and says, what is the standard for these different composites. And then also what's the standard for the technique? And they should make a how-to procedure for us to utilize to inspect this composite. But sometimes they don't, because they don't have enough information themselves. And I'm talking about the manufacturer of the airframe. Now, the type of composite material and how many layers, because the more layers, the more difficult it is for the technology we're using to penetrate and find the flaw of interest. Is the component curved? Is it flat? Or does it have a lot of geometry? Because if there's a lot of geometry, the more difficult it is to inspect these parts. And also, what is the final use of the composite component? In other words, is it going to be a component that's going to take a lot of stress, a lot of load, a lot of contortion or turning or shearing of the metal, of the composite? Does it have a probability to fracture? So therefore, the techniques that I'm selecting, I have to say, well, if there's fractures in this composite, am I going to be able to find it with conventional radiography or ultrasonics, or do I need to use another technique? So what is my probability of detecting the flaw? Well, that determines the equipment. And am I going to use radiography, ultrasonics, or another technique that's more sensitive, because they're coming out with other things that's better, like shearography testing or thermography. And maybe I'll show you guys something like that next year if I'm invited to present. So for the equipment that I've selected, I need a calibration standard. The calibration standard tells me, do I have enough sensitivity using this test to find the flaw of interest? Am I going to use a probe or a scanner to find the flaw of interest? Meaning, for ultrasonic, do I use a probe that uses wet techniques or dry techniques? And is the scanner sensitive enough to find the flaw of interest? So what is the type and size of flaw that I'm trying to detect? The location and the orientation of the flaw. Now, some of these terms may be foreign to you guys, so I'm going to show you guys exactly what I'm talking about coming up. For radiography, for the equipment selection, radiography uses an X-ray machine, or we can use something called gamma, which is it's a radiography source that never turns off. It's a source of radiation. Now, if I'm using a camera or a machine, we can turn it off. And the radiation source penetrates the specimen, and we can capture the information by using non-film techniques, which we call digital radiography, or film techniques, which are using conventional film, just like at the hospital. Now, with digital techniques, we can use computed radiography, which looks like a piece of film because it's flexible, or a digital detector array, which is a rigid device that captures information about the component of interest. Just like the technology that you guys see at the hospital, when you go in to get your, dental work, or maybe an image for yourself. Like a CT scan, a CAT scan, or a PET scan. It's the same technology. For ultrasonics, we can use contact testing. We're actually using a machine that sends electrical current to a probe that vibrates through the material. If we're in contact, we're scanning on the surface, but we're making contact. We can also be careful not to damage the surface. Or we can use a modified immersion technique where we're squirting water at the component, or a full immersion. You're going to see pictures of all of these things in this presentation. For ultrasonics, we have a variety of equipment. We can use a conventional standard flaw detector. We can use what's called a bond tester that vibrates the component, and the vibrations tell you whether there's a flaw or something abnormal or not. We can use something called a C-scan, where you actually get a map of the flaw, or something called phased array, PAUT, phased array ultrasonics, and that can be contact or non-contact. So we're going to see these applications in some videos coming up. Now, when I'm determining the scanner and the calibration standard, well, for radiography, it's a dry test. I take a piece of film, put it on the component, and use an X-ray machine to capture the information. For a scan or conventional ultrasonics is typically a wet test. Whether the part is, I just take a ultrasonic gel, and I use a contact test, or I can squirt water or immerse the entire component in water. The bond tester can be wet or dry. C-scan is typically a wet test where you're squirting water or like a gel at the part. And the phase array ultrasonics is typically wet. We want to try to do it dry as much as possible because we don't want the water to become a contaminant. It could actually seep in and become a flaw. So the test material that we're in for the calibration standard, we want the material and the standard to be the same. So if I'm inspecting carbon fiber, I want a carbon fiber standard that's similar or exactly the same. If it's honeycomb, it needs to be a honeycomb standard. So also the simulated flaws needs to be similar, almost exactly similar to what I'm trying to find. A flat bottom hole is typically used if I'm looking for voids or maybe damage on the inside of the component. And that's the beauty of non-destructive testing. We're looking for flaws that cannot be seen with the naked eye without destroying the part. Or if I'm just looking for a small separation between layers, I can use a standard made of Teflon inserts or an actual flawed specimen. Now, the actual flawed specimen we don't use as a standard, but we do use it as a comparison device. So for the type of flaws that we're looking for, flaw classification, water entrapment or corrosion is one type. And some of you guys that are aircraft directors of maintenance or aircraft mechanics, you've probably seen us bring you a radiograph showing water inside of honeycomb, or maybe you repaired some of these. Or delaminations is a separation at the glue line between two layers. Some of you folks may be certified in composite flaw repair, and you probably fixed the delamination internally. Or it could be hidden damage like cracking or fibers that are separating, or resin, the glue line is separating from the edges, or a disc bond, which could be crushed core or an indentation from a bird strike or something. Crushed core also happens, all of you guys, everybody on this session here, you guys know you cannot walk on certain aircraft wings because you can crush the core with your boot or maybe a tool. So we have to be very careful not to disbond the composite areas. Or impact damage like a bird strike or a lightning strike, or maybe ground handling equipment. If the baggage or the food services guy runs into the aircraft and damages it, we're the people that come out and finds how far is the extent of the damage. Now, both UT and RT is preferred if we can. If the NDI lab has the technology to use both ultrasonics and radiography, that's great. You have something like this image I'm showing you. Use my annotation tool. This is a flaw on a carbon fiber control rod, and it's showing the actual damage on the surface. But a lot of times we can't see this damage on the surface. All we may see is a dent, but you don't know how far the extent of that damage goes. So NDT is utilized to find the extent of the damage that can't be seen with the naked eye. All righty, so I'm going to clear my drawing and let's go to the next slide. So for UT and RT, the reason we need to use both technologies is because if we're using radiography, we can only show you the location of the flaw. We can say the flaw is here, but we cannot use radiography to tell you the depth. We cannot tell you if that flaw is on the surface or located like at another layer. Like we have crushed core on the surface here. We have sheared core, which means it's splicing in half. That's usually from manufacturing right here. But the crushed core is usually something that we do. We damage it with a cart or your boot. A disc bond layer can happen from stress. If the component is flexing and moving during flight, well, it can become disbonded, meaning the glue line separates from the different layers. Now that usually happens in service. However, let me clear these drawings. This splice right here That's usually from manufacturing. The manufacturer did not properly arrange the fibers or the component so that it can bond properly, and, or it can lay properly. Also, we have delamination down here at the bottom. That can happen in manufacturing, or it can happen due to in-service. And here is the wonderful in-service water entrapment. Now, like I said, water entrapment normally happens in service for moisture collecting inside of the composite during use. But hey, it could happen if we use a NDT immersion technique. We can cause water to get in there unintended. So those are our discontinuities. Now let's look at some radiography applications here. All right, so the first application, radiography, well, like I said earlier, we can use film radiography. Conventional film radiography is using an X-ray source film. And so therefore, the X-ray source sends ionizing radiation, which is an invisible beam, through the component. It moves the atoms in the material, and that energy is captured on film, just like at the hospital. And then we chemically process the film, which may take 8 to 11 minutes. And then we view the image on a light box. So I'm going to show you that in the next slide. But nowadays, we're going into two-dimensional imaging using the same X-ray source and a computed radiography imaging plate. So the computed radiography imaging plate is just like a film, except you're using a scanner. You take the imaging plate and you scan it, and you're able to view the image on a computer. I'm sorry, excuse me. The data is sent through a computer and the image is viewed on a monitor. Or a digital detector array, which is a rigid panel. It kind of looks like a TV screen, if you would. And we could use the same technology, use the X-ray source, the ionizing radiation passes through the part, and the atoms are moved. The energy is captured in the detector, which goes through, and the energy is going through the computer and is viewed on this computer monitor. So we're going to see that in the next couple slides here. But we're also now getting into computed tomography. The computer tomography is a 3D image or a slice, just like at the hospital when you guys are getting CAT scans. You know, you can see a 3D image of the component. So this slide right here is me. I'm here on the left. Here I am right here using X-ray film to inspect an aileron. This is on an aircraft in New Jersey. And here's my X-ray machine right here, this orange tube. So the energy travels from the tube through the aileron to be captured on the film. And when we process the film, here is our image on the right, is viewed on a light box. So you can see some water entrapment right here. We've got some resin right here. And this right here is the center of the source. So in order to capture this image, I had to kind of take a skewed view on my light box. But on my, if I use my computed radiography system on the monitor, I don't have to take a skewed view to show you that image. This is an image directly from the computer screen. And look how clear that looks. You can clearly see the water cells and also other water cells here. Let me just get rid of that there, water cells. And also the resin is very clear. So the lighter areas is the resin or the glue line that's intended. But these other areas that's kind of odd off to the side, that's unintended water entrapment. So as you can see, using digital radiography, you can get clearer images and it's better shown on a computer screen than a light box. So for radiography, we're typically looking for a crushed core as shown here on the left, and also a little bit of damage from the top. So we can show crushed core from the side and crushed core from the top with radiography, but we cannot tell you the depth. That is the issue there. So here's an image of me providing training at Gulfstream Aerospace. So this is a cassette. Let me just show you with my tool here. Here is the cassette. There's film inside of the cassette. Actually, I believe we're doing computed radiography for this one. So there's an imaging plate inside of this cassette to protect the imaging plate. And this is an airframe spar. And then we're showing the distance to the x-ray tube. So this image up here is the x-ray machine. And we all leave the room, close this door over here, push x-ray on, and the energy from the beam passes through the component and is captured on the imaging plate. Now, of course, I do have images of that wing spar, but since we're talking about composites, let's take a look at a composite computed radiography image. So this is a computed radiography image from a composites manufacturer. And on the left side here, you can see the structure is clear. Basically, other than, but these are some artifacts over here. These are fingerprints. These are called artifacts, but pretty much this is a pretty clean area. But if you go over here to the left, to my left, anybody can see that this composite is wrinkled. So the manufacturer was squeezing this component together to try to make it fit, and there you ended up with wrinkles, and that is not acceptable. But we also have some holes, and some of the core is splicing a little bit, and we have some wrinkles over here. And we also, now this over here, this is normal. These areas over here, that's normal structure. So as an NDT person, you have to know the difference between what's acceptable and what's not acceptable. For digital detector array, I was telling you guys about that. We are using digital radiography. This is a digital detector array technique. And let's see if we can get this thing to go. So there we go. So we're using real-time radiography to inspect this. This is a helicopter blade, a composite helicopter blade. We're looking for voids between station numbers and the chords. So we numbered the chords on the helicopter blade. We numbered them from 0 to, I don't remember, I think it's like 140. And between splices 100 and 105, you guys can see this real-time digital detector array. There's a splice there. Whether they intended to put it there or not, all we do is find it and tell them that it's there, and the manufacturer will determine whether the indications meet or exceed their requirements. And see here in 115 to 120, there's a splice there. But like I said, the manufacturer will let us know or determine whether that's acceptable or not. And let's just go all the way down to the end here. Oh, this one is actually beyond 140. So we went a little bit further there. This is component, how it's made, splices there, and other resin shown here. So like I said, this is called rigid panel digital detector array using radiography. And that's really cool because it's real time there. So now, stand by one moment. All right, let's go to the next slide here. So now for ultrasonic applications, we talked about radiographic applications, and you can see that we can tell you where the flaws are, but we cannot tell you how deep they are. So the wonderful thing about ultrasonics is it can tell you where the flaw is and the depth of the flaw. Now, if we use conventional contact testing, like I said earlier, the search unit is placed on top of the specimen right here. For contact testing, that's great because it's kind of fast and it's easy and anybody can learn how to do it. So you can see the electrical current is passing from the transducer and it's traveling through the part right here, and it bounces back for a return signal on screen. The problem is we have the signal, which is the back of the core, but we also have noise in between. So the sound is bouncing around inside there, and it gives you unwanted false indications. Now, if we're looking for a flaw like the lamination at the top of the core, it doesn't allow the sound to transmit. So maybe that's easy. But if we're looking for flaws throughout the specimen, we may have a problem. So now we got to use a different technique, like resonance testing. This is using a bond tester. In this case, we're using the Olympus Bond Master machine. So we have a choice. We can use a wet scan or a dry scan. So this first technique is the wet scan. I'm using a conventional ultrasonic transducer that's shown here. This is a calibration standard here with Teflon inserts. It has artificial flaws. These white square blocks are my artificial flaws there at each layer. Well, why do I have them at each layer? Well, I have them at different depths so that when I'm doing the actual inspection, depending on my screen, I can compare it to the standard and determine approximately what depth or what layer the flaw is in. And also I can make it for different sizes. So I can have these Teflon inserts, different sizes, different layers, and also different designs to match the flaw of interest. So for the actual inspection, once I calibrate, I've calibrated the machine to show good areas and areas that we don't want. So what we do is we calibrate and we null the instrument in air. We take the transducer off and we null it. So the air signal looks like this dot right here on the screen. And then when I put the transducer on the part, here is the dot will move to the center of the screen, which means it's bonded. So here's a good area. And if the dot moves off to the side in different quadrants, 1 to 5, the quadrants 1 to 5 match the Teflon inserts 1 to 5 here. So that can tell me approximately what layer the flaw is in inside of an unbonded area in a multi-layered laminate. So that's pretty simple technique. So that's the type of screen we would have for a wet test. For a dry test, we can use many different styles of probes. And I'm going to show you a couple of little videos here. The frequency that we're using, see, as an NDT inspector, I have to choose the appropriate frequency that can penetrate through all those layers and find the right flaw. And if I'm using a dry test, I have to be conscientious of the scanning technique. I make sure I have overlap. Well, really, we do that for wet and dry, but I have to be careful I don't scan too fast. So I have to control my scan speed, how many passes. I have to scan my indexing, which is my overlap. Use the same calibration standard as the flaw that I'm trying to find, and evaluate it and compare it to, my cal standard. So on this picture I'm showing you here is comparing a good area. This is my dry probe that's scanning over a good area compared to a disbonded area. So on my left side, this is called a pitch catch probe. It transmits sound into the material. And so you see the sound traveling through the material, but it only goes so far. So if I lower the frequency from 100 kilohertz down to 5 kilohertz, I may actually be able to penetrate the backside. So the thickness of the specimen tells me the frequency that I'm going to use for my technique. So I transmit the sound through, and also the receive side could tell the difference between the transmit and the receive. So any interruption that stops that energy here will give us a signal response, because I'll have an imbalance between the transmit and the receive. So over here to the right, I have a disbond here. You guys see that? I have a disbond shown there. And you can see the changes in acoustic energy from the left side there to the right side here. So the disbond stops the transmission, and it's going to give me a signal on my screen. I can set up the test to show one type of signal versus another one. So here's one type. This is a quick little video that shows you one type. Here it is. So if I have a good flaw, a good area, the signal's going to look like this. But if I have a flaw present, it's going to give me a larger size signal. Let's check out this little quick video. So the person is scanning over the flaw right here. So watch this. See, there's no couplant there. It's a dry scan. And then if he's in a good area, he had that one small signal, and the bad area shows a larger signal. There it is.
And then it's appearing on the PC as well.
So he had it on a signal on the flaw detector here. Let me go back here. Here we go.
Then it's appearing on the PC as well.
Let me go back one more time. This is showing on the actual flaw detector, and then he has it connected to a PC computer.
And then it's appearing on the PC as well.
There it is on the PC.
You know, we could save that to hard disk tagged with XY encoder positions and Bob's your uncle.
So there you go. We have an indication. So I have another one that's actually a live video, and it's coming up in just one moment. So, you know, that was one type, it's called a RF signal. So that RF signal showed me the top and the bottom, or small size, medium, large signals. But this impulse technique is actually pretty sensitive. We're going to see a quick video of the signal changing from the top of the screen to the bottom of the screen. And if the flaws are bigger, we're going to have a larger size signal. And the smaller the size, the smaller the signal. So small signal versus large signal. And if we have a trace that has no indications, then that means the area is good. Here's the video coming up on the next slide. Let me just set us up here. And here we go. Okay, we are recording now.
Okay, we have 1 inch of composite, armor composite from the Navy. We have 2 inch, 1 inch, and ½ inch holes. Running at 45 kilohertz. And here we go. We'll see if we can find, whoop, there we go. Alright, there's your ½ inch holes. Your 1 inch holes. I'll do that again so you can see the screen.
Okay.
That's the 1 inch holes, and as the depth varies, let's go back to the ½ inch holes. As the depth varies, the height of the indication will vary, as well as the amplitude and phase, the phase change. And in the 2 inch holes. Whoop. Bingo. Okay.
All right. So that was the end of that video. And so this video was actually myself and my good friend and mentor, Mr. Ed Dukich, he was the original co-author of this presentation. I made this presentation for the IA a few years ago, and I've been modifying it over time, you know, to add more advanced technology. So we co-authored this just on ultrasonics, and then I added more information on radiography. So thanks so much to Mr. Ed Dukich from Level 3 Resources, a good friend and a mentor. Okay. So here we go. So we started off this presentation development. You can see us there, co-authors down at the bottom there. We started this presentation development just to focus on ultrasonics and composites, but over time, since I think it was 2011 when we made this presentation, we've actually been developing some more advanced techniques and applications. So let's check this out. So I am the examiner for NASA Marshall Space Flight Center in Huntsville, Alabama. And when I became an examiner for those guys to help with their certifications, now, of course, those folks have doctorates and degrees that I can't even spell. But as a National Aerospace Standard, NAS 410 Level 3, I have the skills and capability to be an examiner to help them with the certifications. One of the techniques that they use for some of the advanced composites they manufacture, like this one here, this is a carbon fiber. Over here, let me just get my annotation tool so you can see. So over here off to the right, this is a advanced carbon fiber skin, and they have flaws, as you can see over here to the left, simulating different layers, depths of the component they're going to manufacture. And all of these are the flat bottom holes. These are drilled flat bottom holes of different sizes, different layers, and different depths. So what we do is we use a wet phased array ultrasonic technique to detect the different flaw sizes here, as you can see, all of these. So the screen I'm showing you below is not the actual scan. It's an example of delaminations using different technologies. So the first one here is an A scan. The A scan can only tell you the amplitude as a signal, the height as a signal, and the location of the flaw. So the location is the horizontal axis, and the amplitude of the received signal is the vertical axis. But that's the only information you have, so you got to be very skilled to compare that to the part. Now the B-scan application here, the B-scan shows you a cross-sectional view or a side view. So it shows you where approximately the flaw is if you had the component on its side, kind of like that's shown right here. But the C-scan shows you a top view. It's also called a plan view. So if I flipped it, it actually shows you the top side here, this top side view, like you're looking from the top down. So if I flip this over, which is what's shown here over to the right, you can find the flaws without even seeing these layers here. And that's the purpose of NDT, to find the flaws that you cannot see with your naked eye. So Gulfstream actually has a pretty cool C-scan technique for the Gulfstream 580 bulkhead. So those of you that are here that work on Gulfstream aircraft, you know, you may be familiar with the COM scan. That's an interesting term there. And it used to be a radiographic technique, and you would bring your aircraft to Gulfstream and they would x-ray it and tell you if you had corrosion at the 580 bulkhead location. But now we're using ultrasonics. So over here to the left, my left, is a computerized screen of the 580 bulkhead area, and on the right is the actual setup. This is my good friend, Mr. Daryl Fuller, who's performing that test and who helped develop these mouse inspection, the MAUS mouse inspection technique. So now back to NASA. So NASA has developed some really cool advanced techniques like this wheel probe application. You see that this is a wet test using phased array. Phased array can send different angles from 0 to 70 degrees. So remember I was telling you if you want to see something at a different angle, it can show you flaws that are flat or at different angles from 0 degrees, which is right here, all the way to 70-degree angle. So we can find those splices. So this is a calibration standard with flat bottom holes and squares of different sizes at different depths, you see? So using the A scan, B scan, C scan that I just showed you, you can say approximately the depth of those flaws and location. So here's an actual scan of that one of those fancy composites that they manufacture. So on the right is the calibration standard, and on the left is the actual top section of the Space Launch System SLS rocket that's going to Mars. And they're using this robotic system here with a wheel probe to scan this surface. The only thing is this is a wet scan. It will be really awesome if we make that into a dry scan. So stay tuned, boys and girls. More to come. So as I come towards a conclusion here, I'm going to show you some other advanced techniques. Like this is one at a place where I'm in level 3. So I'm just kind of showing you this quick video. Let me optimize it a little bit there. Here we go. So there's no words, no one's talking in this video. So the place where they manufacture composites, just one company for different airframe manufacturers. This is a cowling. Remember we talked about engine cowlings? When those cowlings are manufactured from new, we use ultrasonic squirter techniques. We're squirting water, a water column, forward and aft, along the entire length and width, this part with an overlap there. And we're finding the flaws that are over here to the right. Sorry about that. The video stopped for 1 second here. Let me just Okay, get it going again. All right, so there we go. So over here to the right, if you can see my mouse over here, we can find up to 70 different indications that are manufactured. So all of these blue dots right here represents a possible flaw. So I have to calibrate this machine to detect all of these flaws at different layers, different depths, different sizes, different designs. So these are all the flaws that the manufacturer requires us to find. Now, let's go to the next one here. We could take the composite and dip it in water. This is a 5-axis immersion phase array tank where we take this huge airframe panel, immerse it in water, and then we use the scanner device to scan along the every axis, forward and aft, left and right. And we're looking for all of these flaws that's manufactured in this carbon fiber skin. All these squares and rectangles here represent flaw locations. So, you know, because water can cause water entrapment in the manufacturing process, and we don't want to sell people parts with water in it, some newer technologies come out for composites such as air coupled UT. So this is a air coupled UT technique that's made by a company called Sonotech out of Germany. And you know, over here to the right, you have these transducers, and it's sending ultrasound from the left to right. It's called a squirter technique, but not with water. There's a column of air. So this white area right here is the composite. So we have a C scan, remember the top plan view image of a good composite on the right, and a composite with a flaw in it on the left. So we can find these very small discontinuities using air without water. And that way we can avoid water entrapment. So the advantages and disadvantages of radiography versus ultrasonics of composites. Well, over to the left is an X-ray image, and over to the right is an air-coupled UT image. You know, for the X-ray image, we can see the milled information easily. We have the term Sonotech, that's the name of the company. We have elongated flaws and rounded flaws. You can see them easily. And on the right, you can actually see the depth of, and also other little flaws that can't be seen, like all of these little gaps here, all of the adhesive bonds, we can see that, or excuse me, adhesive disc bonds, we can see better, as opposed to we cannot see that glue layer in the X-ray image. So RT advantages over UT. We have the RT image over the right here. This RT image is showing all of these cells. We can actually see the cells of the honeycomb better. With the UT, sometimes we can't see it so well. So the advantage of RT, you can see the cells better over UT. And now the next slide here, UT advantages over RT. For RT, we can show you the location of the flaw, but we cannot show you the amount of resin or the depth of the resin around the flaw. But this phased array ultrasonic technique, you can see the location of the flaw and the mucin resin. It can also tell you the depth. So now this one company called Avacam Digital RT Services and Sonotech, they have combined their technology for computer radiography here, as well as ultrasonics. And they said, well, why don't we take a UT image and an RT image and combine them together to make an overall image. So they said we can get the best of both technologies by combining the technology together. So they've made a technique where they can do both of those using a robot at the same time. Isn't that cool? Well, my friends, our time is up, and I'm sure you have plenty of questions. Many of these terms that I've used may be, a lot of questions on your brain now. So therefore, I just want to offer our information. If you need to contact us and ask us any questions, just send an email to Toni at TB3NDT.com. And you can visit our website, www.tb3ndt.com, for more information on TB3NDT. Thank you so much for coming. Have a great day.